Okay, so let me start. Um, I'm going to start from the basics. So of course, I'm going to consider Dirichlet series of an over n to the s of the form. I'm going to assume these following things, usually assumed in Selberg class: analytic continuation and only possible pole if there is one at s equals 1. And I'm going to assume Ramanujan conjecture, which makes a lot of things easier. Maybe it can be improved if when it is not, but we haven't looked into it very carefully because at certain places we have to use the representations are tempered, which is the same thing as this. And for the forms that I will be considering, there will be holomorphic forms that keep appearing, which will appear in some cohomology. So one knows this conjecture in that case by due to several people. I mean, joint work of several people. And I'm also going to assume the functional equation, which is normalized from S to 1 minus S. So, and then it has an Euler product. And then, of course, you have the standard examples. If I'm going too fast, please stop me. I'll be happy to talk to you about it. And feel free to ask questions. Okay, so of course, we have the Riemann zeta function, and then we have the Dirichlet L function. And then the L functions have a modular form F. And then you see the Euler product, the Euler factors. I put approximately because for P dividing the level, of course, the factors will have a smaller degree. So I'm not being completely precise, so it has degree 2, and then in general, we'll have degree n. For pi, which if you think of as in GLN, it's degree n. And whenever we go to GLN, it's easier to think of automorphic representations for me. For GL2, you can think in either case, either form. And then we are interested in the central L values here. Okay. There was a really nice talk I heard earlier on subconvexity. So this is kind of a revision, but I just wanted to say very quickly. So you have the automorphic L function for a cuspidal representation pi. So this is if on a group G. Of course, even the definition of an L function is not completely obvious for pi on an arbitrary group G, like the unitary group. But if you can relate the group to GLN, then you can use that to define the L function. So for example, if you take the unitary group, then after going to an imaginary quadratic field that is related to the unitary group, then you get GLN, so you can define the L functions. So I will not get involved in that. It's not difficult, but anyway, and then you assume, so functional equation on holomorphic continuation, and that together with the Fragment-Lindelof principle says that you have a bound, which is the convexity bound. L1/2 pi is C of pi to the 1/4 plus epsilon. And of course, the Lindelof is very strong, that it says it's even bounded by C of pi to the epsilon. So what is C of pi? C of pi is the analytic conductor of pi, which is if you don't change the weight, if you keep the weight or whatever at infinity constant, then it is really just the level. But you have to also look at the Archimedean factors, and that gives you a conductor. And for example, I'm using the definition of C of pi given in the Iwanian-Sarnak paper. So, so Lindelof is too hard. So subconvexity conjecture, it says that L1/2 pi is bounded by C of pi to the 1/4 minus delta for some delta. And of course, it has a lot of applications to it, like the work of Duke and then Philippe Michel on the equidistribution of CM points on Shimura curves, and then also for QE, and then together with the Watson formula tells you, so the measure tends to the uniform distribution measure, so that, and then another application is sometimes to non-vanishing problems. But I should say that subconvexity by itself doesn't always imply non-vanishing, because to prove non-vanishing, you need some lower bounds. Okay, So, all right, and then also about positivity, this is the other question we'd be interested in for our, so we're going to look at some special L functions and look at these problems. And so besides subconvexity, we'll also be interested in positivity. And whenever, in some sense, you're in a self-dual situation or self-conjugate situation, the value L1/2 should be non-negative. And it's known in many cases, like, like for example, and it has many consequences too. Like there is an old result of lambda, which was generalized by Iwaniec and Kowalski, which says that if the L1/2 chi for a quadratic character attached to an imaginary quadratic field is non-negative, then you get a lower bound for hk, d to the 1/4, which is great because we don't know any power of d. So therefore, it's not a trivial thing to prove this. And then Lapid and Rawlins proved that if you take any cusp form, which is generic, means has a Whittaker model, and SO2n plus 1, then you have a non-negativity. So I say positivity sometimes, but it's greater than or equal to 0. And then the Walsh-Paget formula, one knows also L1/2 f, the Rankin-Selberg L function of a holomorphic form times, or could be mass form too, times theta series. And he proved that that's in approximately, with controllable factors, the square of the certain period, and so you get non-negativity from it. And then also the Watson Ichino formula, which gives a formula for the triple product, also in terms of the square of some periods, and that also implies it's greater than or equal to 0. And Eris-Lapid has proved that if you take this tensor product doesn't exist as an automorphic form. It's a big open question. But if you take a pair where pi1 is orthogonal and pi2 is symplectic and look at the Rankin-Selberg L function of pi1 cross pi2, then he proved that this also at the center is non-negative. And then there are certain L functions which admit period integral representations. So essentially, this is kind of going to be the same thing that we're going to try to do, is to relate the L values to certain periods, squares, and then times some controllable factors. Okay, so that's our goal. Okay, so if you take any reductive group G, you can just think of G as GLN or the unitary group. And then you take a subgroup and you take a cusp form on G. A period, by a period, what we mean is that you take this form and you integrate over the appropriate quotient of the subgroup. So when I write the bracket H, I mean, so if you're comfortable with the Ardels, it's the Ardels modulo H of Q. It's H of Q is a discrete subgroup, but you can also, it's essentially the same as taking the real Lie group H of R divided by gamma. And if you take the form that transforms according to a maximal compact in a simple way, then you can also relate it to an integral over this symmetric space modulo gamma. So for the unitary groups U1, the symmetric space is just the ball, unit ball in Cn. Modulo gamma, where gamma is a suitable congruent subgroup. So it's essentially, so the period is really taking this automorphic form and integrating it over such a quotient. Okay, so that's what we mean by period, but it also is a period many times in the geometric sense, because many times the cusp forms can be represented by differential forms. And then this H mod gamma is some subspace, which is a cycle, so you can integrate the differential form. So you do get a period in the sense of geometry. So it makes sense to call it, but of course, people often consider a more general notion of a period where sometimes it's not even related to such a geometric thing. In our case, it is geometric. Okay, and then a cusp form, we say, is distinguished if this integral is non-zero, if this period integral is non-zero, distinguished relative to H. Okay, and then So sometimes these period integrals are related to special values of L functions using some Rankin-Selberg type integral. And then sometimes it also characterizes the property, this period integral non-vanishes, means that this form phi is actually a lift from some other group. So that's kind of interesting. That's one of the reasons people study periods in the theory of automorphic forms. Of course, here I'm going to stress the more of the analytic aspects, but okay. So for example, to give one example, you can take G to be GLN plus 1 cross GLN. And then you take H to be GLN, which is embedded inside GLN plus 1 cross GLN, as GLN, of course, embeds inside GLN plus 1 by just taking the matrix G and then putting 1 in the diagonal at the n plus 1th level and zeros off of it. And so here you embed it the usual way in GLN plus 1. And then on the GLN, it's the 1. So, I mean, diagonal. So this is the diagonal embedding. So if you take the L1/2 of the Rankin-Selberg period, then it is known by the Rankin-Selberg theory to be approximately the period of phi tensor phi prime. I've written, what does it mean? Just phi is a cusp form on GLN plus 1. Phi prime is a cusp form on GLN. And then you take the tensor product as a form on the product, and then you integrate over H. So this is sometimes called the Rankin-Selberg period. Okay, and then I want to give an example also. Okay, so if you take any quadratic extension, let's say imaginary quadratic, if you want, and then you take G to be, so this GLN over E you can think of as kind of a group over Q. It's called restriction of scalars. And then GLN over Q itself is a subgroup of that. So you can show that if you take a cusp form pi on G, it's distinguished by H, say, suppose, then it comes from a cusp form on some unitary group. I'm mentioning it for two reasons. One is to show that the non-vanishing of periods implies something strong about the form. It's not every form is going to have a non-vanishing period. Often it's 0. So it's to prove that it's non-zero is not trivial many times. And then it's also interesting that somehow there is a duality sort of between GLN over Q and the unitary group over Q. So if one has a period over one group, then it's a base change from the other. So there's a duality also that is expected in the other direction. So this period is called the Flicker-Rowles period. So okay, this is just some examples of periods, Rankin-Selberg, and okay. Now there's these Bessel periods, which we would be interested in. So let me say what they are. So you have the E is a quadratic extension of Q, and then you take a Hermitian space of dimension n plus 1, and W is a non-degenerate subspace of dimension n, and then you look at the unitary groups associated to B and W. Then you take G to be UV and H is UW, and then this H is sitting inside G, induced by the W sitting inside V. So you can think of it as UN inside UN plus 1, if you want. So we're going to be interested very soon in U2 inside U3. I just wanted to say some things in general because there is nothing special about U2 and U3. So now I'm going to assume that my cusp forms are tempered. It just means that it's like saying Ramanujan conjectures holds. As I said before, we need to assume that for various things. Then if you take these tempered cusp forms, then you can look at this period, which is you take phi of H times phi prime of H over H. So so this is the period. You take essentially what you do is that you have a phi on form on G, you restrict to H. So the restriction of a cusp form to a subgroup is very complicated in general. It's not trivial. or if you like geometrically, take a function on the complex ball of dimension n, you're restricting it to a kind of a dimension n+1 ball sitting inside it. And then it can be really complicated. It could have Eisenstein series and all these things. But one of the basic things that works to help us in general is when you go from un+1 to un is not too small and it's not too big. So it's just kind of perfect in that you have some multiplicity 1 results, and it makes them what people call Gelfand pairs. And the fact that so many things are done for un cross un+1 is because un is their Gelfand pairs. If you take u2 inside u4, it's next to impossible to study because it's too small in u4. Okay, so the Bessel period is you just take a cusp form on G and you restrict to H, and then you multiply it by phi prime, which is on H, and then you integrate it. Okay. So this period is very important, and that's what comes up for us. Okay. Now, I also want to talk about a little bit about the Ghosn-Gross-Prasad conjecture. By the way, after this, I'll pause for a moment to see if people have any questions before I start with the results. So, so now you have a tempered, meaning Ramanujan holes, cusp forms on UV and UW that we just talked about. And as I said, unitary groups become GLN when you go up to the imaginary quadratic fields. And using that, why do we want to consider these base change? It means that that allows you to define the L functions. That's why. As I said, if you just take a cusp form on a group G, there's no reason, there's no one particular L function naturally like GLN. But when you relate it to GLN, you have some. Okay, so the GGP conjecture says that if you take this period that we defined just now, which is the Bessel period, and then this Bessel period is non-zero if and only if the L1/2 of pi e cross pi e prime is non-zero. In fact, this is what we're going to mean by L1/2 pi cross pi prime, as I said before. So somehow the L value being non-zero, they said it's equivalent to this period being non-zero. So this is kind of generalization of the work of Wolfsberger. Because when you take U2, then that's essentially like GL2, and U1 is like taking the units and elements of norm 1 in an imaginary quadratic field. So this is very much like Wolfsberger, and GGP is short for Ghosn-Gross-Prasad. This Prasad, of course, is Dipendra Prasad, because we have two Prasads who are famous mathematicians. So, so anyway, this thing here, this conjecture is known for by, so for n equals 1, in some cases of n equals 2, it was done by Neil Harris, who was a student of Ghosn. And then Wei Zhang did a refinement under some local conditions. Now a recent result of Bazar-Plessis, Liu, Zhang, and Zhu, they together proved, the first batch of people have proved this conjecture for the case we're interested in, like U3 cross U2 and more generally, but they proved it for tempered forms which are stable. So there are some forms that are not stable that come in a weird way from subgroups. And the second group of people, Bazar-Plessis, Chaudhary, and I'm blanking out on the third name, and they did this unstable case. So anyway, in all cases that we need, they've proved a condition. They proved this result, and they proved even something called Ichino-Ikeda type result. So what it is that, so here it says that the period is non-zero if and only if the L value is non-zero. But you can ask, is there a formula that relates the L value to the period? Exactly. So Ichino and Ikeda made a precise conjecture. And they proved, and we say here formula of that type because they proved that it is equal up to some local factors, which we have to control at the bad factors. So up to that, then this is kind of known. And that is very useful to us because we are interested in the L value. So the reason is what we're going to do is to, get some averages of these periods, Bessel periods, get information about it. And then the fact that the Bessel periods are related to the L values is due to these people. So we make use of that. And so that allows us to prove results about the L values. So, okay. Maybe I'll just say the goal and then maybe, so as I said before, what happens is that if you, in the case UW inside UV, let's say V is dimension 3 and W is dimension 2. That's the case we're going to study. Then what happens that this period that I just defined, the square of the period divided by the Peterson norm of phi and phi prime. Phi is a cusp form on UV, U3 if you like, phi prime is a cusp form on U2. So the Peterson norms come in the denominator, and then you take the square of the period, and then you can sum. What we're going to do is the sum. If there is anything maybe non-trivial, what we do is we are summing over phi over the bigger group, not the smaller group. So like it's somehow a little bit easier to sum over the smaller group. So when we sum over phi, this sum here somehow comes up in one side of Jacquet's relative trace formula relative to G relative to H. So, so we want to, so this formula, relative trace formula defines, somehow describes this. And then some Ichino-Ikeda formula, some asymptotic version of it, then that we prove precisely what it is and that this is equal, then this period here normalized by the Peterson norms is some positive constant we can explicitly compute times the L value here. Of course, it uses all the people's results from before, but we also have to do some extra to get this precise result because we need to study the matrix coefficients at bad primes and estimate them. So, and this tells you actually, this gives you the positivity of this L value because it is related to the square or something, and everything is positive. And then the subconvexity comes by expressing this in terms of something. So this will come from what we call the spectral side in the relative trace formula. And then the geometric side has to be analyzed. And then it also will also get a lower bound for this, and that will give us some non-vanishing results. Anyway, okay. All right, is there any questions so far? Or I guess none. Sorry if it looks complicated, it's not. So let me try to be more specific. So we take an imaginary quadratic field, q squared minus d, and then we take a three-dimensional vector space, say with the basis e minus 1, e0, e1. It's a standard way to write it, and you have a Hermitian form. Let's just take this matrix here. I mean, there are various ways to do it. This is a skew Hermitian, but anyway, so it's a Hermitian form. And then you take the U2, the unitary group for this form, and G prime is U1, 1. That's the unitary group of the subspace defined by E minus 1 and E1. So there's a natural embedding here of U2 inside U3, which ABCD goes to this U3 this way. Now, let's say for simplicity, n is an odd prime inert in E. You can easily kind of extend it to square free, but let's say for simplicity, it's an odd prime that's inert in E. Then an n prime, let's say, is some large enough odd prime that is split in E. So n is going to be the level of the form on U21, and n prime will be the level of the form on U11. And then you pick k as an even integer. So, excuse me. Sorry, my phone started ringing. Okay, so you have a cusp form on U11, that's pi prime, or phi prime is a form that generates this representation pi prime. And then pi infinity prime, I'm going to assume it to be holomorphic type of weight k. As I said before, U11, SU11 is SL2. So you can think of this pi prime as just like a holomorphic new form of weight k and level n prime. And then on the U21, we also take a holomorphic form, but it'll be a holomorphic discrete series of this particular weight, minus k, k plus k over 2. So due to some orthogonality principles that will enter, you will only be able to relate, our method will only relate things of certain weight relationships. So as you notice, the U21, these weights are given by a pair of integers. It should be minus k, k over 2. And the period, of course, is the Bessel period we looked at before, p phi phi prime. So what we proved with Philippe Michel and Liyang, so what we proved is if you take a phi prime, which is a new form, like classical new form of weight k, but now you take this some orthogonal basis of holomorphic forms on U21 of this weight at infinity, trivial character, and level n. Then if you take the sum here, so what we prove is that, and the right-hand side is what we get out of the geometric side of the relative trace formula. So it's going to get n squared over n prime squared minus 1 plus big O of n prime minus 2, and then you get another term. So you get so essentially what happens, and maybe I should tell you, when we use relative trace formula, if I have time, I'll say a bit more later. Then what happens then on the spectral side, you get certain double cosets. There's indexed by certain double cosets of G, the rational double cosets, G of Q modulo H of Q on both sides. And then there are really three types of double cosets. One is the identity double coset, and that's one term. And then there's also a unipotent double coset, which is kind of like parabolic, as we say classically. And then you have kind of regular double cosets, toric, and which are like what we call hyperbolic in the classical case. So, and what happens is that we can do each part very carefully, and then we get this asymptotic formula. Okay, so, I mean, we get an asymptotic formula and we can then estimate certain things. Then I just wanted to say for GL2 cross GL2 cross GL2, there are many people, I'm sorry, there are these dot, dot, dots that should include many names because there are many results. But so there was, anyway, various people. And this is kind of similar to GL2 cross GL2 cross GL2. So in the triple product case, the degree of the L function is 8. Here, actually, the degree of the L function over Q is 12, actually. So it's a bit complicated. And I should also say, like this was pointed out by Blomer in his talk, so when you take UN cross UN plus 1, in general, there is a result of Paul Nelson on the spectral side. It's a spectral result on the subconvexity in the spectral aspect. What we are trying to get here is in the level aspect. We get something called a hybrid. I call it what I call hybrid subconvexity. But anyway, you get an exact thing. And then I want to tell you the left-hand side, the period is, as I was saying before, related to the L values that we're interested in. So that's the point. Okay, that's what I'm repeating here. So, but I want to be a little bit more precise. So this result that we know is that the period square divided by the Peterson norms, you get certain L functions, which are the most interesting one is the one on the top, L1/2 pi e cross pi e prime. There are some special constants, and you divide by the, so the denominator L functions are in the GL2 case, it will be like the symmetric square L function. So that's what happens for pi prime, but for pi, it's a different one. It's degree 8 L function, but it's manageable, and the value is at 1, so we can understand it and bound it well. It's not complicated. But the difficult thing actually is certain bad factors. We have P sharp phi phi prime, and that involves matrix coefficients, these bad primes, bad places. And that involves a lot of some hard work. And that's, so somehow we can get something, and then first you get these results here. When you substitute, you get this, but then we have to estimate this bad factors as well after you've done the earlier result about the geometric side. Okay, so what we prove is that the local factors, the P sharp V, so they're roughly 1 over k minus 1 times n prime squared minus 1. So it's kind of nice. It's approximately that. I mean, you can be more precise, but anyway, it's positive. And that implies L1/2 pi e cross pi e prime is non-negative. So it's kind of important. So up to this point, everything else, so, okay. So anyway, that's the result about the non-negativity. Then the other result is that when we deduce from all this is that the sum over pi of L1/2 pi cross pi prime, so the one what we're interested in, then we divide by these very standard L values at 1. Then this thing here has an upper bound and a lower bound. The upper bound looks like k n 3 plus epsilon plus something very small, and then also the lower bound here. So as you run over this family, and then where you're fixing pi prime, you're averaging over pi, then this is what you get. You get a certain bound, but this bound is not so great, but it's pretty good. The lower bound is good, and that gives you some non-vanishing results, that many of these L values are non-zero. So we get, if you precisely see how things go with n prime also, then the L value, what we get is that once you prove positive non-negativity, you can bound each L value in the sum. Then you get that the L1/2 sum here is bounded by this complicated looking thing. Its k is like the weight from infinity, and n to the 3 plus epsilon, n prime to the epsilon. Then another term here, and this kappa is essentially, it's something very simple that I won't say right now, but if you want, I can tell you that. But anyway, so that what happens is that to get subconvexity, what you have to do is you have to be kind of, it's important here, is k times n prime cubed is at least c times n to the 4th plus epsilon. So if you're in this restricted range, so we're not doing it arbitrarily, that's why we call it hybrid subconvexity. So if you're in the restricted range, you increase, n and n prime can both go to infinity, but you have to do this, then you get this thing here is bounded by c to the 1/4 minus delta. So you do get subconvexity if you're in this restricted region. So it's not an arbitrary plane, but it's in a restricted region in the plane. Okay, if you think of n and n prime. So, and also k, you can also vary k. So either k or n prime has to be large compared to n. That's the condition. Or you can fix one, whatever. And then this is of course, the analytic conductor of the complete L function. Okay, and then I should have mentioned before that analytic conductor is like k to the fourth n squared n prime to the sixth. So the 1/4 will be k n to the 1/2 n prime to the 6/4 or 3/2. So what happens is that this allows you to say that L1/2 pi cross pi prime, if I vary n prime, then our method consisted of averaging over pi, but after the non-negativity, we got bounds for each one. And then now if you vary n prime, then what you get is that you get n prime to the 2/3. Actually, it's kind of very interesting, I think, because it gives a subconvexity bound, and the conductor in the n prime thing is like n prime to the 6th. So the convexity bound is n prime to the 2/3, but we get n prime to the n prime to the 3/2 is convexity bound. N prime to the 2/3 is less. In fact, this also beats the Weil's bound. It's even less than the Weil's exponent in this special case. So when you consider this big L function and you vary let n prime in the n prime direction, it's better than Weil's bound. Okay. And then here, of course, remember our n prime is split in the, it's a prime that is split in the imaginary quadratic field. So anyway, so this is kind of strong, like the second moment on GL3 cross GL2, the GL3 form fixed. Okay. Okay. The consequence of these results and the subconvexity bound, by the way, please ignore this L fin that I've written here, because we used to write L fin and then Philippe suggested we remove fin and just write L, because we used to sometimes write L for the complete L function. So it's really just the usual L function. So ignore the fin and just think of it as L. Okay, so it says that if the number of pi you're interested in this space or in the orthogonal basis here, and then you want the L function of 1/2 is non-zero, how many are there? So you can actually say that it's greater than or constant times a maximum of this number that you have here. So that means that it at least exists. So you get something non-vanishing result. But you get something, anyway, so that's, but we had to struggle to just get non-vanishing because, anyway. Okay, so is there any questions at this point? Because I thought I would say, if I had time, something about how the relative trace formula comes. Maybe, okay, sorry about, I know it's a bit technical, but I don't know. Maybe I can make a couple of philosophical things. You know, the relative trace formula is used a lot, and trace formula and relative trace formula is used a lot in representation theory, but very often, so that's again, you get spectral side equals geometric side, and kind of a philosophy typically with the Langland school is to not actually compute the geometric side, but actually always have two groups, and then you show for some matching functions the geometric sides are equal. And then you get a correspondence between the spectral sides, and that allow you to prove a lot of results about lifting, for example, symmetric square lifting or various things. You can prove using trace formula if you compare the so what, in some sense, this work is a much harder generalization of an earlier thing I did with John Rogowski, where we reproved the result of Duke about some averages of L values, really about GL2 cross a torus, which is the same as essentially U2 cross U1. And what we had to do was we decided to actually try to compute the geometric side explicitly. And what happened was we found that you get some dominant terms, which was very explicit, but then you get some error term, coming from these hyperbolic terms, and the explicit formula is kind of ugly, but nevertheless we could bound it. So then we realized that you could use that to prove results about bounding L values by using the relative trace formula. And anyway, that's the basic idea. So let me just say very roughly what the relative trace formula is, then just for a few minutes, and then I'll stop. Okay, so anyway, so if you take a nice function on G, forget that I've written Adels and so on to be precise, but you could think of the, just in the classical setup, instead of Adels modulo Q, you can think of reals modulo Z. Same thing, just minor differences. So if you work with level 1, you can completely, if you work with level 1, you can completely avoid Adels. But in general, it's better to use this. So anyway, you take a function on the group, on the Lie group, which is nice properties, and it's compactly supported, and it's a test function. It defines an integral operator. I'm going to divide the group by its center because the center is always a big problem. It's kind of like if you have GL2, when you divide by the center, you have PGL2, which is kind of similar, but not the same as SL2. But so then when you take if you integrate against this function, you get an operator on the L2 space of G mod gamma. So I'm going to think of it as G mod gamma. Then what happens at this, of course, now can be represented by the kernel function, where you take f of x inverse gamma y, and then you have a spectral decomposition of this kernel function, which is the cuspidal part, which is called K0, and the residual part, that means, I'll come to that in a minute, and then the Eisenstein part. The Eisenstein series contribute to a continuous spectrum, and that gives a very complicated thing. Often you have to subtract, and that's part of the difficulty. And then the residual part is really everything in the discrete spectrum that is not cuspidal. So for classical case, SL2R mod SL2Z, then the residual part is just the constants, nothing else. But they get more complicated for U21 and bigger groups. Anyway, so you have the spectral decomposition, so that allows you to decompose the kernel function in different ways. Now, even before so this is just the thing here. For the usual trace formula, I should say something. What you do is that you take this kernel function, you integrate over the diagonal. You take this, so this function is a function of 2 variables. So you can think of the kernel function as a function on G cross G. Then you have G sitting diagonally in G cross G. If you integrate this kernel function over the diagonal, then you get the usual trace formula. Because you can expand it in 2 different ways, spectrally and geometrically. So, so Jacquet's idea was, the relative trace formula, was not to integrate over the diagonal, but instead take some subgroups H1 and H2 of G and then integrate over H1 cross H2 instead of the diagonal subgroup. That's what the relative trace formula is. And the interesting thing is, if you choose, for example, G is GL2, and then you take the H1 and H2 to be the maximal unipotent subgroup, which is like 1 star 0, 1. And then if you integrate over it according to some characters of this maximal unipotent group N, then you actually get Kuznetsov trace formula. So Kuznetsov trace formula and Peterson trace formula are special cases of the relative trace formula. And what happens is the Kuznetsov trace formula has a lot of complications because of the Kloosterman sums and bounding them. But if in the relative trace formula, if you take some other groups, like for example for GL2, this is what I realized with Rogowski was, if you integrate not over the unipotent to get Kuznetsov, but instead if you integrate over some torus, which is compact torus, coming from an imaginary quadratic field, then the terms you get are much more manageable. They're easier. So and something like that happens in this case as well. Okay, and so anyway, so you have these separate things, And what this tells you in the middle is how you integrate the kernel over the subgroup. And then on the right-hand side, on the left-hand side, the spectral side, you get all the periods. On the right-hand side, you get the sum over the elements, the geometric things, and what are called orbital integrals. And then the test function is kind of complicated, but we have to use the matrix coefficient of the discrete series for U21. And this formula we just took out of Wallach's book on representations of Lie groups. And then we take some very special things. And the key point, I'll come to the key point. Maybe I'll just skip a little bit because I'm run out of time, maybe are running out. So the geometric side, when you have this sum over the various types of terms, you get some orbital integral type decompositions. And what happens is that in this case, U21 here, if you look at the double cosets, G relative to G prime, sometimes I write H, sometimes it's G prime, it's the same thing. Then the double cosets are like this. They're either the identity coset or this gamma E, which is like this, of gamma E of X. And then these are elliptic elements, where X is in the imaginary quadratic field modulo elements of norm 1. And then they form a complete set of representatives for this double coset space. So what happens is that, like I was saying before, the geometric side becomes there is an identity double coset, unipotent double coset, which is gamma E of 1, and then everything else, which I call regular. So to be precise, some people would call this regular and semi-regular, but which is not identity or unipotent. And what happens is that these first two terms give you the dominant terms in the asymptotic formula. So the orbital integrals, the identity type, we have a very precise, so I'm going to come to that. This will be the last slide I'll show you. The identity type, it's very explicit. We can compute it explicitly, the orbital integral. Unipotent type, you can compute it, but you have an explicit formula which is very ugly, but you can bound it here. So what happens is that both these terms look like dominant terms. But luckily, the identity term dominates the unipotent term in the asymptotic formula. So the second one is subsumed by the first. And then the regular terms, they give you the error terms. That's it. So I think I'll stop. Oh, actually, I should go to the last page. Thank you, and happy birthday, Balu. All right.
Are there any questions for the speaker? If not, then we can thank Dinakar again, and all our speakers for the day.
Okay. All right. Thank you.